So we're going to see human-centered ML, why we need it, and how we can go around it. So there is a set of guidelines on how to incorporate artificial intelligence and machine learning into products and decision-making systems. And those set of guidelines, they set a number of factors that we need to test in order to ensure trustworthiness analysis of the AI model. So we can see, for example, accountability, which is required to ensure responsibility of the system and the outcomes. We need to ensure technical robustness and safety, and this is based on the principle that we need to mitigate also the risks arising from using this technology or the technology not performing as it was predicted. Oversight, the ability to understand the system and audit in particular the system, privacy and data governance, and we know how it's important to handle private data, sensitive data, and machine learning models. They are powerful in memorizing this information, and therefore they can be exploited by hackers. Non-discrimination and fairness is important. And also we need the model to be transparent and give explanations, and we're going to see later why and how. And of course, these factors, they also need to ensure that the system works for societal environmental well-being. So these factors are related to each other. So I'm gonna speak in particularly about technical robustness and safety, as well as discrimination and fairness and transparency. And some of these dimensions, they will also relate to accountability and oversight. So a lot of my talk is inspired by healthcare applications and what is the current state of the art, and how we can use and how we can translate what is the advances of current machine learning models into safety critical applications is quite important. So the first thing that we need to realize is that in clinical practice, in order for a clinical decision support system to be used, needs to be both internally and externally validated. So internal validation is what we know that relates to the reproducibility, what we do in our everyday research in order to understand the performance of the model. However, a model, consider, for example, a classifier of MRI images, when this applies to data from another hospital, the scanner will be different, the protocol, the MRI protocol would be different, and this will create shifts in the distribution of the data that will affect generalizability. We also, in the middle between external validation, which involves different geographical position and occasionally also different population, different kind of population, is a temporal validation, which relates to the same centers, but with different time points compared to the data we use to train the model. So when we look into the clinical practice, we see that it's not only important to see the performance of the system, as we know, as accuracy, precision, F1 score, and confusion matrices, but actually we need to understand how to calibrate the system, and we need to evaluate the agreement between observed and predicted risk estimates. We also need, it's typically in clinical systems, the discrimination is estimated based on the receiver operating characteristic curve in order to take into consideration different thresholds of specificity. And finally, we are going to see we're going to talk about clinical usefulness, and we're going to see how this it is subjective, and it depends not only on the machine learning model, but of the context of the questions we need to solve. So let's go on assessing calibration. So as you can see here, usually this is done by plotting the calibration curve, and that's simply the observed events of interest with relation to the predicted risk. And normally on these decision systems, a perfect system would be considered if it has an intercept of 0 and a slope of 1, and if the observed predictions are higher than the predicted risk, we say that the system underestimates the risk, and conversely, if it's lower, then we say that the system overestimates the risk. So sometimes having a perfect intercept and a perfect slope, that won't give us a perfect calibration, and that's the reason why the clinical scientists look into the curve and not just the estimates of the intercept and the slope. Also, it's important to understand that behind this we need an adequate sample size, and that depends on the kind of the model that is used. So if the model is, for example, a simple logistic regression, you would expect that you need 200 patients. But here we should realize that this is 200 patients with the incident event or the disease, along with 200 patients without the incidence event and the disease. And is estimating the desirable sample size for more complex system, it can be challenging. But let's see an example. Let's see an example of a prediction model that has been developed with clinical settings. And this is a simple prediction model based on logistic regression analysis. We can see that has been internally validated, typically with cross-fold validation, 10-fold cross-validation here. And it has been also validated with data from external hospitals and centers. Psychosis is a complex psychological disease characterized by delusions as well as depression and hallucinations. And what the clinicians want from this model is to be able to predict which patients they will respond well to the medication. Therefore, there won't need to keep those patients medicated for long, because this has severe side effects. So that's the clinical utility of the model. And going forward, as I said before, typically in a clinical scenario, you will see the calibration curve. Here you see with the black line the calibration of the model, and you see with the red line which has been fitted to the model. So when we say calibration in the large, we mean external calibration. And normally that will examine the intercept of the model, which is the mean between observed and the difference between the mean observed and the mean predicted estimates. And the calibration slope usually is mostly focused on the overfit, and this is estimated with internal validation. And on the bottom, you see the distribution of the subjects as well here. So the model performs reasonably well. Now, let's say we put a more complex model in this, let's think about deep neural network. It is quite simple model. It has 2 layers with an ReLU activation followed by dropout for regularization, and a final dense layer with a sigmoid in order to be able to estimate the risk estimate from 0 to 1. So now, if we go and see the AUC curve, we see that we managed to get the multi-layer perceptron performance is slightly higher than that of the typical logistic regression. And now, it might, if we had more subjects, we would be able to do better than that. But if we go and see the calibration results, then we realize that the linear regression model performs slightly better than what we have done with the deep neural network. So miscalibration of deep neural network is a known problem. And it has been work done which tries to understand how miscalibration occurs and how that relates with different choices of the architecture of the model. And in these graphs here, I show you the expected calibration error. And the expected calibration error is a summary statistic estimated by looking into the difference between the accuracy and the confidence of the model. And you see how the expected calibration error compares to cross-entropy error, which we typically use to train the deep neural network. Varying depths, the cross-entropy error will fall up to a point, and whereas the expected calibration error, it increases. And the same happened with varying number of filters, convolutional filters per layer. We also use, it's quite commonly when we use convolutional neural networks to use patch normalization in order to improve the training by changing, regularizing the distribution shift within the neurons. But here we see that the expected calibration error increases, although the cross-entropy error has decreased. With the weighted decay, it's very popular for regularization, effectively L2 regularization within the model, and it's used to control the overfit. And here we can see that this is the case where actually the cross entropy and the expected calibration entropy follows similar curves. So what we observe effectively is a disconnect between the cross entropy loss and the expected calibration error, and that reveals an overfit. So although the deep neural networks, we know that they perform, they are complex models, nevertheless, we think that is relatively immune to overfitting. The calibration error says a different story, that the classification might be immune to overfitting, but the probabilistic error, it's still affected with overfitting. Um, and going to the clinical consequences that I told you before, here, a simple example is to consider the detection of breast cancer as a use case. So we know that it is quite important to detect cancer as early as possible. So a model with a greater specificity and even slightly worse sensitivity could have a better AUC, but it can be a worse choice for a clinical decision system for breast cancer detection. Therefore, that shows that we can't just use performance blindly to compare models and choose a model without considering the scenario this model will apply to. So somebody would expect to do decision analysis and to take a number of factors in consideration, which they have to do the health outcome, like the number of complications prevented or the quality adjusted life years saved. So the reality is that we don't have this data with our training data, and it takes years to collect them effectively. So another way to look at it that clinicians have used is based on net benefit. So the net benefit looked into how the threshold probability affects the benefit that the model is giving us. And let's go here and see an example of this decision curve analysis on the problem we discussed before, the psychosis linear regression model. So effectively, the net benefit is plotted against different threshold probabilities. And these threshold probabilities tell us whether somebody will weight the risks of not applying a particular treatment versus the risk of applying this treatment to a patient, and which would have been the threshold to choose one over the other. So here we see that the horizontal line is when we choose to treat none of the patients, and that has zero net benefit. We see here a gray curve, which in fact is when we choose to treat all the patients, because these are standard policies in clinical practice. We see also a curve with a red line, which is based on treating based on the duration of untreated psychosis alone, which we know the duration of untreated psychosis is a factor of how well a patient will respond. And finally, we see also with the blue line here the net benefit of the logistic regression model used for prediction of psychosis. So now, to decide which of those classifiers, which of this method is better, we need to take into consideration what is the treatment probability threshold. And this is subjective, and it requires expert knowledge. So in this case, NHS consultant psychiatrists, they have been consulted, and they provided an estimate that their threshold of treating or not treating a patient is between 40 to 60%. And if we go here and see the net benefit for 40 and 60, we see that the prediction model in this case outperform the other methods. So the threshold probabilities here, we can also see them as odds. So consider, for example, the scenario you have 10% threshold probability in the cancer detection case. This means you have 1 to 9 odds So it's 9 times worse to miss a patient than actually detecting a false positive. Here we see a few other examples that they show how the curves vary with relation to the specificity and sensitivity of the classifier. So we see again treating all versus, treating none versus treating all. And then we see how a nearly perfect classifier with 99 specificity and 99 sensitivity would perform. And here we see a specific classifier which with 99 specificity and 50% sensitivity. And here we see the other way around into sensitivity and specificity values. So from there, another factor that we should consider when we need to make a decision is the uncertainty of the model. So we know that the Bayesian framework offers a principal way, an intrinsic way to account for model uncertainty. And we can easily realize that just having point predictions of a system is not enough in order to trust the decision of the system. And here an intuitive example, which shows the posterior distribution of 3 individuals, 3 patients, plotted against the prediction score of the model. So you see that for patient A and patient C, if the threshold is 0.4, whether you treat or not treat the patient, it's quite clear that one patient is positive and the other is negative. For patient B, though, if we take the mean or median summary statistics to estimate the point prediction, we will see a value of slightly above 0.4, whereas if we take the mode, this value would be slightly less than 0.4. So adapting a system without really understanding the uncertainty of the system, it means that we cannot really trust the decisions. And uncertainty can be also demonstrated, as you see here, with the gray area along with the calibration curve in order to help understand better whether the system is certain for its prediction. However, uncertainty in deep neural networks, it's not trivial to estimate, and there is a lot of work trying to create Bayesian deep neural networks, and that has given some interesting results. However, it also is affected by the complexity, and that can make the problem harder to solve. However, there are breakthroughs, and this is an interesting work that the researchers, they used dropout, and they interpret it as a Bayesian approximation. And the dropout objective in this case, it relates to what you've seen, what you've heard in previous lectures with relation to deep Gaussian processes. And because they showed that they can minimize the KL divergence between an approximate distribution and the posterior of a deep Gaussian process. So effectively, what they tried to do here is they sample a set of vectors given from a Bernoulli distribution, and subsequently they create a Monte Carlo estimate. And this is equivalent of performing stochastic forward passes through the network and averaging the results and estimating also second order moments. in order to understand better the variability of this. And you see on here on the image how uncertainty is reflected in the decision of the deep neural network. So this is a classifier where it has been constructed in order to recognize digits. And at the bottom, you see the input images, which is just a line which rotates. So when the line is almost vertical, then the model with high certainty detects that this is a digit of 1. However, if you go a few columns around here, the model starts detecting that the digit is 5, but the uncertainty is very high. So let's now go and look into how some of what I mentioned can also link to discrimination and fairness, and how we can construct measures to evaluate this. So first of all, to give you some examples of algorithmic bias. So one example, it goes back into 1980s, where in a medical school in UK, they decided to create an algorithm to make the admission process fairer in the university. However, it happened exactly the opposite, because the algorithm was learning based on previous data. And in those data, there was prejudice against female as well as racial minorities. So it was not, so it was a surprise for them. They didn't do it intentionally, but effectively the algorithm has learned to discriminate. And the fact that that wasn't made intentionally, it made it far more difficult to detect. Another example in face recognition in 2018, there were evidence that there were a big error rates across recognition systems that have been developed from big companies like IBM and Microsoft. And the error was showing that it was far more accurate to predict male white males accurately rather than Black women. And the reason behind it was simple. The model simply hasn't been trained with enough data from these subgroups, and therefore it wasn't able to generalize its performance to those minorities. Another example is from discrimination in online ads offered by Google. We all use Google for our research. So in 2015, showed that if you search for CEO, you get 11% only of CEOs that are women, although the percentage in US of CEO women is much higher, is in fact 3 times higher. It also came up that if a woman was looking for jobs, wouldn't get the high paid jobs, would get less, whereas a man would, if he was searching for jobs, would get jobs with much higher potentials. And the reason for that was because Google was using historic data and preferences, and therefore the system was biased based on that, and reproducing this, bringing that forward. And you can see that that can affect the perspective people have as well. So we know that there are discrimination laws for unfair treatment, and it's not allowed to discriminate based on sensitive attributes such as gender and race. However, those features, they might be implicitly correlate with other attributes. Another example with racial bias in healthcare came in 2019, where actually there was an algorithm that considered Black people healthier than white patients because its predictive ability was based on healthcare costs rather than illness. Therefore, naturally, Black people were poorer and they wouldn't spend as much money. So how this happening? So basically, the scientists plotted the number of active chronic diseases across the risk scores of the model, and they realized there was a discrepancy between white people and Black people. And in fact, to get assigned to this healthcare program, a Black person needed to have much higher illness than a white person. So these programs were designed, in fact, in order to detect people that they are in greater need and offer them the healthcare they need. And because they are so expensive, they couldn't admit everyone in those. So how do we go around with machine learning? How we can guarantee against discrimination bias, especially when those are not intentionally programmed into a software. And there is research here that it looks into calibration within groups and tries, for example, to match the expected output with for white people with relation to Black people, what is called statistical parity. However, there is a fundamental problem with this approach that has to do that in certain cases, the incidence of a disease, of an event, it can be naturally more often in one subgroup than the other. For example, if you have depression, might be more common in women than men. And therefore, you cannot really bias the probabilities to be equal because that will create also a bias on the risk of healthy people. There are other ways, though, with relation to looking within of these subclasses. For example, the balance for the negative class or the balance for the positive class, which they look the average score received by people that are positive with relation to the outcome in this case. And they try to make sure that it's the same in each group. So let's go to the last factor that I mentioned, which is about transparency and explainability. So we know that explainability is quite important in decision-making process. In particular, it's a fundamental human right to know why a decision has been made for them. So any decision-making system should take this in consideration in order to be able to trust it and be used also in terms of legal frameworks. And this is the reason why explainability has been exploded. The research in explainability has been exploded the last few years. So, but explainability is context specific, and it can relate can relate to different target audience. For example, it's different explanations that a clinician would look into a model and different explanation a patient would like to know. Explainability also can help data scientists in order to improve the product and detect what is wrong with it. And it is also important for managers that they want to understand how to invest, how to improve the investment in healthcare and the provisions. And similarly, it's also important for regulatory and legal purposes. So thinking simply about it, let's say we have a use case where a patient is female, is 85 years old, and her BMI is, let's say 32, and she doesn't smoke, neither drinks alcohol, and the system tells her that she needs to get medicated. So is it just enough to provide the this decision and follow the decision? We still need to understand how the model came to the output, and do we know the condition and cases where this model is successful? Do we know what is the factors behind this particular choice? So in clinical practice, we know based on previous research, specific factors can affect a disease, whether it can be modifiable factors for a person, and apart from age, which is an important factor in heart failure, large BMI can also increase the probability of a heart incidence, as well as other factors like smoking and alcohol. So a system that detects these factors across all patients, we can see later that what it does is basically constructing a global explainability model. And we can also have representation learning to help us understand not only which input factors affect the output, but also what is the specific function of the system, and what are the latent factors that affect the decision process. It's easy to see that some models are intrinsically interpretable, and they have been used many years, like decision trees and linear models. They have been used in clinical practice because of that. But however, we also realize that we can take advantage of more complex models. And in that case, we need to explain and invest more time in explaining them. So there is a lot of work trying to categorize these models. And they can be model agnostic or model specific. They can give global or local explanation. They can be ad hoc, like representation learning models, or post hoc models that they explain a model that is already trained. They can be surrogate functions that try to approximate simpler functions, that try to approximate more complex model, or as we're going to see, there can be visualization techniques, in particular for deep neural network, where you visualize the gradients. And these are the type of models I'm going to focus more. And I'm going to focus on global and local explanations, because it's important to know, at least in healthcare, the factors that contribute to a decision in general across all patients, what we call global explainability. But it's also important to be able to give local explanations to the patient of why this decision has been taken for him or her. And also, we're going to very briefly look into model agnostic and model specific. Model agnostic can help us to compare different models, different machine learning models, but model specific, they might be able to give us better idea of the underlying function or malfunction of a classifier. So let's see an example. So here we are interested in ECG classification, and typically it's quite common to classify heartbeats and segment them. And if you do segment one of those beats, then you realize that consists of some specific features which are well known to the clinicians, and they are important because they relate to the phase of the cardiac cycle. So we thought that if we have here an algorithm which provides us an idea of which of those input features were more important for the prediction, that can help a clinician to trust it, to trust the model better. And we created a simple deep neural network based on a convolutional 1D layers. And in order to understand the importance of the ECG features, we applied permutation feature importance. That's a reasonably simple algorithm where we actually perturb each of the features across all your samples. And by looking into the difference in performance before and after, you can understand how important this feature is. And here, for example, the model would tell us that the QRS, in this case, it came up with a high significant score. So these are explanations which take into consideration all of the samples. Now, if we want to have local explanations, we can use surrogate models, and one common model is the local interpretable model agnostic explanations, where here simply they fit a linear model, and you see here the line, and they try to approximate the function of a much complex model locally. So effectively, here they try to minimize a proximity measure, which relates the model to explain with the surrogate model, and it also includes a complexity factor. And that will allow explanations and retain model flexibility, so you can easily apply it in different models. And here, for example, you see the Lime explanations with relation to logistic regressions. In a sentence, this is not too bad, which tries to characterize whether this is a positive sentence or a negative sentence. And on the right-hand side, you see again the Lime explanation of an LSTM model on the same sentence. So here we can see that the logistic regression is not able to capture the relationship between words, in particular not and bad, which they have both negative meaning if they are used separately, but in this scenario, they have positive meaning. When we go to, when I talk about model-specific explanations in deep neural network, I talked about visualization methods. This is a very common example, which is the gradient-weighted class activation map technique, GradCam. It's very popular. And what it tries to do is to visualize and backpropagate the gradients with relation to specifically the decision that has been taken. So it is applied in the last layer, and it does a kind of global average pooling, and then backpropagates the activation with relation to the decision all the way to the input, in order, in this case, to highlight the pixels which are related to a specific decision. So it's a relatively simple technique that can tell us where a network is looking at. And in this case, for example, we applied it on ECG classification, and this gave us a more fine way to characterize the importance of each time point. Now, the problem with these methods of these explainability methods is the fact that it's difficult to compare, and there is no ground truth. So we don't have a very good idea of what is a good decision and what is not a good decision. And for this reason, researchers, they look into properties that attribution should have. And these properties, like sensitivity, for example, it has to do with the fact that if the prediction does not depend on the input feature, then the attribution to that feature should be always zero. The implementation, and this is a property that actually is violated by the GradCam method that I showed you before. They looked into implementation invariance. So the output of two models should be always identical regardless of their implementation, which is a property that GradCam has. Completeness, though, is a property that guarantees that the importance score will not vary significantly with small differences in the input. And this is another property that GradCam doesn't have. Linearity, as we know, if a model is a linear combination of two models, then the explanation should be also a linear combinations of the explanations of each of the models. And symmetry preserving that symmetric variables with identical values should achieve identical attributions. So in order to construct such a system, they use integrated gradients. And integrated gradients, they considered a path between a baseline and an input, and they integrated the gradients along this path. So effectively, here, if we consider that I is the features, in this case, features can be time points or pixels if we think in terms of images, and X is our input image, whereas X stretch here is the baseline. What we do in order to estimate the integrated gradients is we generate signal interpolations between the baseline and our input. And then we calculate the gradient prediction with respect to these input features. And we use a Riemannian sum to average the gradients. So that was a principal way to visualize gradients, but it suffered from the fact that you have to choose a specific baseline, and usually the baseline chosen is zero. However, in certain cases, zero might still have information, and in that case, the explanations won't be valid. And that's the reason, that's what expected gradients tried to solve. But a more important reason I show you expected gradients is because they use the attribution as a flexible framework to encode priors. So in fact, they use the explanation and they showed that by doing that, by combining the explanation priors within the prediction framework, it can improve the performance of the model. And here we can see, for example, that this has been encoded based on omega, which represents a log transformed prior probability distribution over possible attributions. And I'm gonna show you this slide, which is what is considered the vision of the next generation in clinical decision support system. So here we see that the model needs to be able to provide intuitive explanations that involve the representation of the model, and they are provided to the human in a way that they are understandable and within the context of the application. But it's also important to understand that an explanation should be, well, a model should be also improved by the human being in the loop and providing evidence of whether the decision of the model is appropriate in this case or not. So here we can see also this feedback loop. So I'm gonna leave this here, and I'm gonna show you also some of this material has been inspired from a course on informed clinical decision making using deep learning, and you can find some of the slides and the references there, along with more notebooks on explainability. Also, I would like to point out that there is currently there is new work and new guidelines in healthcare which actually tries to investigate how to incorporate artificial intelligence-based decision support systems. And this is quite nice job, nice work to understand better the intersect between clinical research and machine learning. Thank you.